Welcome back, students. In the last lectures, we have described real gases and phase changes from gases to liquids and liquids to solids and all that good stuff. Today, we will begin to study liquids and solutions. Liquids are very different than gases. While gas molecules can be approximated as being non-interacting, we cannot do the same thing for liquids. Liquid molecules are in physical contact with each other, meaning that they must interact, and we have to use that interaction when we try to describe systems with liquids or solutions. In this lecture, we will do our best to begin to describe liquids, noting that every liquid-liquid interaction is unique, making it challenging to obtain general rules for their behavior. This is very much like it was challenging to get a general rule for real gases, as real gas molecules are all unique. We'll start today by defining the ideal solution. The learning goals for today are going to be to describe ideal solutions and also talk about how real solutions aren't quite ideal. We'll apply Raoult's law, which is the defining factor for ideal solutions, and then we'll learn to read PZ diagrams. We'll take a brief look at TZ diagrams, but our focus will be on PZ diagrams, where P is the pressure and Z is this interesting term that's looking at the mole fraction of both vapor and the liquid phases. It may seem pretty strange, but to understand how solutions behave, we will start by considering the vapor pressure. So in a liquid, there is a propensity for the molecules to evaporate, that is, to escape the liquid phase and go into the gas phase. This is held back by their intermolecular interactions. So molecules with a strong intermolecular interactions, like water, are not very volatile, or molecules with pretty weak intermolecular interactions are very volatile, something like acetone or ether. And we have to take this into account, taking into account the pressure of molecules in the vapor phase is a way to describe their intermolecular interactions. So, like we mentioned in the beginning, we cannot ignore the intermolecular forces for solutions, and we can define this with the vapor pressure. So, if we have a solution, so not only a liquid, but a solution, what kind of molecules will be in the vapor phase? Well, we can think of the solution as a collection of molecules, as is shown here. And what's happening in this solution is that molecules on the surface would be able to escape into the gas phase. So if you have a pure liquid, it's only going to be one type. But what if you have a solution? Well, if you have a solution, the number of molecules that are likely to go into the gas phase, it doesn't really matter what's going on down here. It only matters what's on the top. And so we'll use Raoult's law to define the likelihood that a molecule in solution will enter the gas phase. So we're going to say that Raoult's law is the partial pressure of each of the components in a solution is equal to the vapor pressure, and we saw this before, we'll give it this P star symbol, of the pure substance multiplied by the mole fraction. So we can write this mathematically, and we'll do that here in the next click, but what does this mean? This means that the vapor pressure, right, this is this idea of how likely a molecule is to escape the liquid phase. We need to multiply that by the mole fraction, which is a good approximation for the amount of molecules that will be at the surface. So if our surface is 10% toluene, and toluene has a certain propensity to escape the vapor phase, it'll be reduced by 90% if only 10% of the molecules are on the surface, compared to if it was pure toluene. And so we can write out Raoult's law is Pi equals Xi, the mole fraction, times Pi star. So here, Pi is the actual partial pressure, Xi is the mole fraction, and this Pi star is the vapor pressure of substance I. Any solution that obeys Raoult's law is ideal. So what kind of solutions are going to obey this? Well, let's think about that for a minute. What affects how molecules escape the liquid phase? Well, I just mentioned it a little bit ago, and it is the interactions of those molecules with the other molecules in the liquid phase. So for this to be true, this is saying that the only thing that matters is the vapor pressure of the substance and its mole fraction. For this to be true, what we need to have is that the AB interactions, or the solute-solvent interactions, are the same as the solvent-solvent and solute-solute interactions. So if toluene has a certain vapor pressure, that means it escapes interacting with other molecules of toluene with a certain propensity. If we put that in a solution with something else, it would need to have the same interactions with that other thing in order to escape with the same vapor pressure, with the same propensity. So you might imagine that a solution of toluene and benzene, both pretty similar molecules, would have pretty similar vapor pressures, pretty similar interactions, and obey Raoult's law. But maybe a solution of toluene and hexane, or toluene and some other more complicated organic molecule wouldn't. And that is, of course, the case. So what we'll see as we continue on in this lecture, that most solutions, if I were to grab any two liquids and try to mix them together, do not obey Raoult's law. And even those that do kind of obey Raoult's law are not perfect. And so we'll continue through the next few lectures thinking about this, discussing this, and ultimately coming for a good model for how we can describe most any solution. When a liquid and vapor are together in equilibrium, their chemical potentials are equal. If this weren't true, either the vapor would go into the liquid phase or the liquid would go into the vapor phase. So what we can do is set their chemical potentials equal to each other. The chemical potential of the substance I in solution is equal to the chemical potential of substance I in the vapor phase. And we know how to describe the chemical potential of a vapor in a mixture. It is the chemical potential under standard conditions plus RT natural log of Pi over P naught. If we had a pure liquid, we could describe a chemical potential in a similar way. So the chemical potential of the pure liquid would be mu I star, which would still equal mu I naught, but then the pressure would be the vapor pressure rather than whatever the actual pressure is in the solution. We can substitute these things in and set them equal to each other. So the chemical potential of substance I in the solution is equal to the chemical potential of substance I based on its vapor pressure plus RT natural log the partial pressure of substance I divided by the vapor pressure of substance I. And using Raoult's law, we can substitute in the mole fraction times the vapor pressure for the partial pressure and come up with this expression here, that the chemical potential of substance I in solution is equal to the chemical potential of substance I based on its vapor pressure plus RT natural log of the mole fraction. Now, this is basically the same derivation that we did for gases, and that means that these liquids that are obeying Raoult's law are mixing in the same way that gases would. So we can describe the delta G of mixing, which is always negative since the mole fraction is a negative natural log here. The entropy of mixing is always positive. The enthalpy of mixing is always 0. And another weird thing that we'll see in the future is that the change in volume upon mixing is also 0. So substances that obey these are hallmarks of ideal solutions. Now, what you'll probably note is that there are many solutions for this, which this is not the case. For example, oil and water don't mix. And even for solutions that do mix, they don't really follow these ideal guidelines. So we'll see in a couple of lectures what we do and how we modify this to try to account for real solutions. We'll now attempt to apply the ideal solution model to binary mixtures. So we'll go through some math and then we'll look at some plots of these things to see how it works out and what we should expect. So the way we'll go about describing a binary solution is first by considering what the total pressure would be. Well, if we only have two components in solution, the total pressure is simply the pressure of substance 1 plus the pressure of substance 2. And we can now use Raoult's law to describe this because we're assuming that Raoult's law is applicable to this solution. So what we can do then is say that the partial pressure of substance 1 is simply the mole fraction of substance 1 times the vapor pressure of substance 1. And then what about substance 2? Well, substance 2 is equal to the mole fraction of substance 2 times the vapor pressure of substance 2. But what we can do instead is add in 1 minus x1. That's going to be the mole fraction of substance 2 there times the vapor pressure of substance 2. So here we have an expression for what the total pressure is in terms of the mole fraction of one of our components and the vapor pressures of our two components. This equation simply states that the total pressure is dependent on the amount of each component in our solution multiplied by their respective vapor pressures. If we plot this alongside experimental data for miscible liquids, and the example that we'll have is benzene and 1,2-dichloroethane, we can see that it does a decent job in describing the experiment. So in the dashed lines is the predictions, and the solid line is the experimental measurements. It does a pretty good job, especially at high and low concentrations. It starts to deviate a little bit in the middle, but I think we would all say that this is a pretty good for dilute solutions, and even in general, does a pretty good job at describing this. This is in general not true. In a couple of days, we'll see some examples of some very wonky liquid-liquid interactions that don't at all look like they're even close to obeying Raoult's law. Since the two components of the solution have different vapor pressures, one is better at escaping the liquid phase in the other. This gives rise to a difference in the proportion of the components in the gas phase compared to the liquid phase. So when we use X up here, this is the mole fraction of the components in the liquid phase. And we can rearrange this above expression into this form down here that clearly denotes what the mole fraction of the substance in the liquid phase is. So to derive that expression that we had before, we simply need to multiply through by x1. So this will give us x1 p1 star, and then we'll have plus p2 star minus x1 p2 star. So I'll bring this p2 star to the other side. We'll get p total minus p2 star is equal to x1 times p1 star minus p2 star. And then we'll divide by that to get that definition. So we'll have x1 is equal to p total minus the vapor pressure of substance 2 divided by the vapor pressure of substance 1 minus the vapor pressure of substance 2. And so this will give us an expression for what x1 is. And remember that x1 is the mole fraction in the liquid phase. But we have actually a different mole fraction for the vapor phase. And so we'll define that using y1. And so y1 here is still a mole fraction, but it's the mole fraction of the vapor phase. And it's simply equal to the partial pressure of substance 1 divided by the total pressure. So we can substitute in for the partial pressure of substance 1, Raoult's law, and for the total pressure, our expression up here. And that will give us x1 p1 star over p2 star plus p1 minus p2 star x1. And this can be rearranged to eliminate the x1. I'm not going to do that. It's not too bad to do. And we end up with p1 star times p total minus p1 star p2 star over p total p1 star minus p2 star. So we have two very different equations that describe the mole fraction for the liquid phase and the mole fraction for the gas phase. Here we can look at how P total depends on x1 and how P total depends on y1. P total depends on x1 linearly, which means there's going to be a linear relationship between the mole fraction and the pressure. But the total pressure depends on y1 hyperbolically, since it's in the denominator. So this gives us two different functional forms for these mole fractions. And here we can see what we'll have. So this is a plot of the mole fraction in the liquid phase against the total pressure, and this is the mole fraction in the gas phase against the total pressure. And what we can see is that, again, like we saw, we have a linear line and we have this hyperbola here. So what do we do with any of these? Well, if we know we're existing at a mole fraction of, say, 0.4 moles benzene and a pressure of 100, we know we're safely within the liquid phase. All our will be a liquid. And again, if we're out here, so if we're at 0.8 and maybe a pressure of 20, we would all be in the vapor phase. The middle is a little bit weird, and neither of these plots actually tell us what goes on in the middle. So on these lines, we are converting between liquid and vapor. But once we cross the line, this model no longer makes any sense because there is no X1, there's no mole fraction in the liquid phase. It therefore makes sense to put these two things together. And this is the PZ diagram that we mentioned in the beginning as one of the learning goals. So if we put the mole fraction based on X and the mole fraction based on Y together, we come up with the following plot. So this is a plot of P, the pressure, against the Z. Z is the total mole fraction, not caring about the liquid or the gas phase. So a Z of 0.5 here for this solution means that we have exactly 50% benzene. We don't necessarily know if it's in the liquid phase, the vapor phase, or a mixture of both, but we know that we have exactly half benzene. These kind of plots are very useful, and we can actually determine what's going on as a function of pressure, which is the easiest thing to change. It's pretty hard to change a mole fraction without manipulating things too much. So let's consider the following pathway. At point A, we're at a Z of benzene of about 0.7. So we have 70% benzene, and the other component of this solution is dichloroethane, I believe. And so we have this mole fraction and this pressure. We're at about 90. We are well above the vapor pressure of either substances, and so our solution is all in the liquid phase. Now, as the pressure decreases, if we decrease the pressure and back off, you'll note that what's going to happen is eventually we go into the vapor phase. But what happens in the middle? So at point A, we're all in the liquid phase. At point D, we're all in the vapor phase. But what about B and C? This is kind of where it gets kind of weird. These plots, we can actually read the information right out of them. So at point B, what we need to do is draw a horizontal line like we have in this image here. And this horizontal line will tell us both what's going on in the liquid phase and what's going on in the vapor phase based on where this horizontal line intersects the liquid and vapor phases. So here at point B, again, our total mole fraction of benzene is 0.7. But in the liquid phase, the mole fraction of benzene is about 0.65. So the total mole fraction of benzene is 70%, and in the liquid phase, it's 65%. In the vapor phase, it's up here at about 85%. And so we can read this information right off of these plots. So this tells us that benzene is better at escaping the vapor phase than the other component of the solution, since more of it is in the vapor phase at any point. Now, as we keep reducing the pressure, what happens is that we get less and less of the benzene in the liquid phase as more of it goes into the vapor phase, and eventually we're all in the vapor phase. Now, this doesn't tell us yet the amount of molecules in the respective liquid and vapor phases. To do that, we can use the lever rule that comes from torque physics. And essentially what we'll do is say that the number of molecules total in the liquid is equal to ZB, the mole fraction, minus XB. And then we have the vapor, the number of moles in the vapor is equal to YB minus the ZB. So rearranging this, we can come up with the following expression: that the total number of moles in the liquid divided by the total number of moles in the vapor is equal to Y minus Z over Z minus X. Plugging in numbers here for point B, we end up getting about 3. This is very approximate. So that means we have approximately 3 times the total number of molecules in the liquid phase as we do in the vapor phase, which makes sense because we're pretty close to the liquid phase boundary here. At C, we might expect it to be reversed. Maybe we're about 1/3, so most of our molecules are in the vapor phase. We can also look at a TZ diagram, which does this in a similar fashion. So the TZ diagram reveals what happens to a solution as a function of temperature. And this is very analogous to what we just saw. So if we start with a solution with a mole fraction of about 0.1, so 10% benzene, what happens if we increase the temperature? Well, as we increase the temperature, we will start to boil the solution. And we already discussed in the last slide that benzene has a higher vapor pressure. It's more likely to escape the liquid phase than the other component in this solution. So what will happen is when we start to boil as a function of temperature this liquid, more of the vapor will be our benzene, our more volatile substance, than the other component in the solution. So we'll boil that, that'll go into the vapor phase. And then if we cool that off, what we'll have is a solution that is enriched in benzene compared to where we started. Then we can do it again and again and again and again and again. And if we do this enough times, what we'll be left with is pure benzene. We will have boiled out the other component that will be left in the liquid phase, and we'll end up with just pure benzene in the vapor phase, which then we can condense into a liquid. We can purify benzene in that way. This is actually a process called fractional distillation. This is how things like crude oil are separated in this kind of complex apparatus where the bottom is heated. And then as this liquid boils, these are heated as well from the heater down to the bottom, but they're heated to less and less and less temperatures. And this is how crude oil is split into things like petroleum and the small organic products that you guys use to do organic chemistry reactions. And all the other different, kerosene and all these other different parts of the oil. Now, this looks really nice when we show it in this way, but of course, this is not universal. So we can do things like separate crude oil that are all organic components that all have similar sorts of interactions with each other. But there are solutions that are called azotropes. And these azotropes actually interact very differently with each other than they do apart. And that can kind of break this up and allow us to not do this. Now, what's necessary for this is you can see that essentially the boiling temperature is a function of the concentration. So here at 0 benzene, the boiling temperature is the boiling temperature of the other component. And down here at 1 benzene, the boiling temperature is the component of benzene. And in between, it's decreases unilaterally, right? It just goes monotonically down until we get to the boiling temperature of benzene. So if we have a solution where there is a boiling temperature in the middle that's higher than either one or lower than either one of the components alone, that's going to screw us up. And we do, of course, see that. So we'll consider an acetone chloroform solution. And I want you guys to pause the video here for a minute and see if you can think why an acetone chloroform solution might have very weird interactions compared to either component alone. So hopefully you thought about this for a little bit. You might not have been able to come up with it, but acetone has an oxygen bonded to a carbon, so it's got a pretty electronegative oxygen. And chloroform has a pretty electropositive carbon, as CHCl3. So what this has is acetone actually has a hydrogen bond acceptor and chloroform has a hydrogen bond donor. Now, neither of them have both, so hydrogen bonding doesn't happen in acetone or chloroform, but in the acetone chloroform solution, there actually is hydrogen bonding possible between the two molecules. Now, what this does is it gives a maximum boiling azeotrope. So there's an ideal mixture in between that has a boiling temperature that is higher than either component alone. And so once you get to this temperature, we can't actually separate past this because at this mole fraction, the vapor phase and the liquid phase have the same composition. So they're boiling at this new high temperature. So we couldn't go from a concentration down here and get one over here. Now, actually, if we had a concentration that was above this, we could purify out one of our components. It's also possible to have a minimum boiling azeotrope that has a minimum here that we can't purify beyond. So this is all I wanted to go into for this lecture. In the next lecture, we'll look at colligative properties, which is what happens to liquids when we add non-volatile solutions to them. And then following that, we'll go into dilute solutions and come up with a model that actually works for more than just, 2 solutions of very similar looking organic chemicals.